Alright, I'm going to do Chapter 4, question number 58. And this one can be particularly tough anytime we get these problems that say, show that this is true. Oftentimes students will struggle with that. And the problem reads, for part A, show that the minimum stopping distance for an automobile traveling at speed v is equal to v squared divided by 2 mu sg, where mu of s is the coefficient of static friction between the tires and the road, and g is the acceleration of gravity. Okay, so kind of a confusing sounding problem, and they also want you to show that something is true. So they give you some information. It's a car that's stopping, okay? So we know that there's f of g, and we know that there's f of n, and let's say it's moving to the right, okay? So then friction would be acting to the left. Now it's important to remember that f of g is equal to mg, and the normal force and the gravitational force are the same. Therefore this is also equal to mg, and since force of friction is mu times f of n, then I also know that the force of friction is mu times mg. Okay, and also in this case, the sum of the forces, or the unbalanced force, is the friction force. It's the only force that isn't canceled. Okay, therefore ma can be equal to the friction force, which is mu times mg. So this goes away, and I know that A is equal to mu g. Okay. Now again, the problem, it says show that the minimum stopping distance is v squared divided by 2 mu g. Okay. So we want to somehow get a displacement involved in this. Now the one thing that we have nothing of, and it wasn't stated in the problem at all, is a time. So from your experience with your kinematic equations, you have a kinematic equation that reads v squared is v naught squared plus 2a delta x. Okay, and in this case, if you're coming to a stop, this is 0. Okay, and we're supposed to show that that particular speed, or I'm sorry, we're supposed to show the displacement given in an initial speed is equal to v squared over 2 mu g. Okay, so we've got to get this in there. Also in the equation, v squared over 2 ug, or 2 mu g, there's no acceleration in there, so we're going to have to make a substitution. Okay, so I'm going to rearrange for delta x, this equation. So since this is 0, I'm just going to get rid of it essentially. So I end up, when I rearrange this, delta x, okay, would be equal to v naught squared over 2a. And then what I'm going to do is I'm going to substitute in mu g for a. So I get delta x is v naught t, or I'm sorry, v naught squared over 2 mu g, where this is mu of s. Okay, and that is showing that the stopping distance is equal to the initial velocity squared divided by 2 mu s g. Okay, now that was only part A of the problem. Part B of the problem says what is this distance for a 1,200 kilogram car traveling at 95 kilometers an hour if mu of s is 0.75. Okay, so using this equation that we just showed was true, delta x, and the initial velocity was 95 kilometers per hour, you'll have to convert that into meters per second, and if you do that, 26.4 squared to the mu value was given as 0.75, and of course gravity is given as well, 9.8, and you end up with a distance, or a displacement, of 47.4 meters. Okay, so that is how you do number 58.